I like these measures that are abbreviated MAD. I like the idea that we take the absolute value of these differences to make sure they don't cancel out. And that is a method that is used. However, that's not the most common way to describe the dispersion in a data set. I bet you've heard of terms like standard deviation. I bet you've heard of terms like variance. The variance and standard deviation are based on a different way of doing something to these numbers to make sure that they don't cancel each other out. Specifically, it's based on squaring these differences. So instead of taking the absolute value of each difference, now we're going to imagine that we're squaring each one. So I'm going to square each of these differences that I have here. Okay. So what am I going to get? I'll get a 4 here, and a 4 here, and a 0 here, and a 16 here. Okay. If I take the mean of these squared differences, that by definition is the variance. That's what the variance is. So if I take these values, add them up, divide by how many there are. We've got a 4 and 4 is 8, plus 16 is 24 over 4 is 6. The variance here is 6. That's what variance is. So why would we square them? How do we interpret this? The problem with the variance is all of a sudden everything's in the squared scale. I'm thinking about how many courses my students have taken before my statistics course, and you tell me the amount by which these students differ from the average can be described by saying that the variance is 6. That's kind of weird because that's based on the squared scale. Now I'm thinking of squared number of courses. What is this number 6? It's the average squared difference between a particular student's number of courses and the average number of courses. Again, it's how far is a particular student's experience from the average squared on average. Trying to say this as many ways as I can because my experience is that one of those ways will click. Okay? So what's important here is that you see what we've done, that you see that we have each value, we're subtracting the mean, we're squaring the differences, and we're taking the mean of those squared differences. What I'm going to do now is write down the same thing, but in terms of notation rather than numbers. Instead of writing down 4 actual numbers that my students might tell me when I ask them how much previous statistics experience they have, I'm going to represent those numbers with the following notation. I'm just going to write y1, y2, y3, and y4. And in our particular data set, we know that y1 was equal to 0, y2 was equal to 0, etc. But now we're going to be more general. Okay? And we're going to make sure we're clear on the notation for mean and median. So the mean comes from taking y1 plus y2 plus y3 plus y4 and dividing by how many data points there are. Or another way to do this would be to use the sigma notation for a sum. In other words, I want to add up all the yi's where the I starts at 1 and goes to n, which is the sample size, and then I want to divide that by n. If this notation isn't familiar to you, the idea is that we are going to take this value that comes after the sigma, and we're going to look at what that value would be for each different thing I could take on. So I first might be the number 1, and then we increment it. I could also be 2, 3, 4, 5, all the way up to n. And we add together all those results. In other words, if I is equal to 1, we'd have y1. If I is equal to 2, we'd have y2. If I is equal to 3, we'd have y3. If I is equal to 4, we'd have y4. And if this n over here is equal to 4, then we should stop. And then we add up these values. That's what this notation means. Add up the value of whatever is following the sigma sign where I goes from 1 to n. So the mean comes from adding up all the values and dividing by how many there are. the variance can be expressed in the same way. The variance can be expressed in the same way. But in order to do that, I want to come up with a Greek letter to use for mean. And the one I'm going to choose is mu. The one I'm going to choose is mu. However, to be more consistent, if I'm going to use mu, what I really should do is replace these lowercase n's with a capital N. And what's happening now is we're touching on a really important distinction between a sample and a population. The distinction between a sample and a population. Capital N is the conventional letter we use to describe the population size. How many people, how many units are there in the entire population? Lowercase n is the letter we conventionally use to describe the number of people in our actual data set, the number of units in our actual sample. So why am I pointing out that we should use a capital N here? The reason is that mu is the notation we use to represent the population mean, the average in the entire population. So if I'm going to use a mu here, I should be using a capital N here to say that this is the average, this is the mean of all the values in the population, not just in the sample. So if I'm thinking of that as the sum of the four statistics experiences of the students in my course divided by 4, that means I'm thinking of the 4 students in my course as the entire population, rather than thinking of those 4 students as a sample from some larger population. So I'm calling this mean mu. So now that I have notation from that, I'm going to find a way to notate the variance. So instead of writing 0 minus 2, as I did before, I'm going to write y1 to represent the value of the first person in my data set minus mu, which is the mean in this data set. And I'm going to square it, because that's what we did with that difference. y2 minus mu squared, y3 minus mu squared, y4 minus mu squared, and I divide by 4. Now I'd like to represent this quantity in terms of this same kind of sigma notation that I used up here. So what we have is the sum, where I goes from 1 to capital N, of yi minus mu squared, because I'm summing that up for each value of I, divided by n. And that's the variance. In particular, it's the population variance, which will notate sigma squared. So just as it's important to distinguish between the sample mean and the population mean, it's important to distinguish between the sample variance and the population variance. This is the population mean. This is the population variance. One more quantity that students typically hear about in an intro stats class, and that's the standard deviation. And we don't have to learn anything else in order to define the standard deviation, because it's exactly equal to the square root of the variance. In other words, the standard deviation is equal to the square root of the sum from I goes from 1 to capital N, of yi minus mu squared over n. So standard deviation is just the square root of the variance. If you know the variance, you know the standard deviation. If you know the standard deviation, you know the variance. It's the same thing. Why would we ever take the square root? Well, the reason is that it's kind of annoying that the variance put everything on a squared scale. I was interested in knowing about how many courses students had previously taken, and all of a sudden you're telling me something about the squared number of courses students had previously taken. So if we take the square root, at least we're back on that original scale. The standard deviation gives us some measure of how far apart students are in terms of the number of courses they've taken, as opposed to the squared of that difference.